Good morning, everyone. So today again we are meeting in your subject, that is Geographic Information System, where we will be studying today regarding the spatial analysis and the data modeling. So let's have a look about the content. So we will be covering the spatial analysis, data modeling concept, surface model, and surface modeling operations. So let's discuss what is spatial analysis and modeling concept. Now, as we have already discussed in previous lectures, that spatial, that is something related to the geographic position of that area. So when we are talking about the spatial analysis, that is the technique to analyze the data in terms of its location. What I told you, that which is related to its XY location, or you can say the geographic location. So the technique which helps us to analyzing this spatial data is known as the spatial data analysis. Using this spatial data, okay, or the technique of spatial data analysis and modeling, we can able to identify or find out different patterns of the data. We can identify different locations based on its spatial location, that this may be this place, because Jaipur is having some different spatial location as far as JNK is concerned. So both are having different geographic locations. So we can identify based on the spatial properties of that particular area that this is this place. We can also go for the identification of different relationship among the features. Okay, so if there is a height, or hard topography, maybe it is some hilly area or something. So that kind of relationship among various features can also be identify different spatial analysis and modeling techniques. We can also plan for the efficient routes. Okay, like in your network analysis, if you go through that technique, we are able to find out the shortest route, or the best route to find out a particular location. So plan which is related to the efficient route planning can be determined. Then we can also perform different kinds of site selections with related to the potential site location of water resources, of habitat suitability. These kind of things we can perform. We can also model or predict the values based on discrete sample observations, etc. So these are few things which we can easily find out with the help of spatial analysis and modeling, where the identification of different patterns, identification of different relationship among features, planning of different routes, identification or analysis different kinds of route, then different kinds of potential site selections, and different kinds of predictions of different values based on different data samples can be observed. Then we can also get if you go through your overlay analysis, or different kinds of identification of this thing, then we have studied one technique that is called as topology, where we analyze different kinds of relationship among different features, in which the proximity analysis, overlapping, intersection, visibility, accessibility, etc. are the major relationship related functions. Then we can also identify the different patterns about the hotspots of different phenomena, outliers, clusters, change detection. So whatever we can think of related to identifying the patterns, identifying the hotspots, identifying the change detection, identifying the different kinds of relationship. So these kind of things we can easily analyze with the help of different techniques of spatial data modeling or analysis. I hope I'm clear about the spatial analysis and modeling. Now we can proceed for the other things which we can done. We can predict the values. Now, what kind of values? With the given set of measured points across an area, we can determine the estimated values of the unmeasured locations. That means we can also identify, or we can calculate the location of a point based on the neighboring values. Okay, so we can predict, for example, some value is missing in for some object, so based on the neighboring values, we can easily predict the value of the missing data. Okay, so based on the points in and around that point, we can um, you know identify the value of unmeasured location. Then, using this spatial analysis, one can combine the information from many independent sources, and they can derive a new set of information by applying a large, rich, and sophisticated set of spatial operators or geoprocessing tools. Okay, so what we can do, we can, as if you go through the definition of GIS, we can overlay different layers onto a single platform, and we can come up with the combined result having different operations applied on that. We can go for the addition, subtraction, multiplication of these layers, and then we can go for different kinds of geoprocessing, or we can use different kinds of spatial operator, which I told you that addition, subtraction we can go for. Okay, so using this spatial analysis, we can combine the information of different sources onto a single platform, and by by applying different techniques, different kinds of spatial operators, different kinds of geoprocessing techniques or tools, we can come up with the different kinds of spatial analysis, which may help us in finding out different kinds of results. Then why we need this spatial modeling? Okay, spatial analysis is clear that we can, with the help of spatial analysis, we can go for the identification or analyzing of different data sets in terms of the different locations. Okay, so with the help of spatial analysis, we can perform different functions which are related to the identification of their and patterns, their relationships, their different kinds of network analysis related plannings, then their prediction about the site suitability index for anything, then for creating different kinds of models, and different kinds of values prediction based on different data sets and observations. We can also find out different kinds of relationships which are related to their proximity, overlapping, intersection, different kinds of spatial operations. Then we can also go for the detection of different patterns, which includes the hotspot outlines and the change detection over a period of time. Okay, then we can also predict the values based on the neighboring values, and we can also go for the spatial analysis by combining different kinds of layers or informations onto a single platform using different operators or different geoprocessing tools. Now, what is spatial modeling and why we need this spatial modeling? Now, to finding out the relationship among the geographic features to understand and address any particular problem, we need a modeling techniques. Okay, so while we need to find out some kind of relationship is there between two features or more features, and what kind of relationships is there. Okay, so that we can address different kinds of problems, or we can go for different kinds of implementation of management strategies. For that we need a model which can be performed with the help of this spatial modeling techniques. Then the spatial modeling technique also allows us to derive new data values from the existing data sets and to predict might what happened and where happened. Okay, so based on the existing data sets or the historical data sets, we can also predict little bit about the future of a particular phenomena, where it can happen and what can what is the intensity might be there for the particular incidents. So that kind of spatial modeling can be done with the help of existing and the present data sets. Then modeling often involve the developing of specialized workflows through programming, creating scripts and automatic workflows lets us efficiently query and process large amount of data for implementing more complex algorithms. Okay, so modeling it also involve the techniques where we are using different kinds of programming based languages, where we are into the creation of different scripts and automated workflows, which is uh, very helpful in different points of queries and progresses of data, which helps us to solve different problems or different complex data problem or algorithm. It helps this kind of modeling. Okay, for example, I need to know a place which has more height than 15 meters. So in my non-spatial query, I will mention this query. Key places, you have a theme, you will select for that theme, you will apply that function that is greater than 1500, look for those places. So after querying this will automatically take out those places on your map, and your problem is solved. Okay, you have extracted the information about the places which are more than 1500-meter heights. Okay, so modeling it often involves some developing of different programming language, creation of different scripts and automated workflows where we can easily get through the problems of complex data sets related problems. Okay, then after this we have spatial analysis modeling related concept, where the model helps us to understand, to describe and predict how things work in real word. Okay, so nowadays we have different kinds of simulation models where we can input the data sets. We can understand the phenomena of the data sets based on those historical data sets. We can describe it, and based on different tools and technique we can also predict how the things they are happening in the real world. So these models they also helps us in the understanding of different data sets, describing those data sets, and also in the prediction of these data set with reference to the real world phenomena. Then the spatial modeling spatial problems involve two different models. Now, what are those models? Spatial modeling or modeling spatial problems involve two types of model. One, the representation of models, in which we have the representation of the objects in the landscape, And the second is the process model, where by simulating the processes in the landscape. So we have two types of model. One where we are representing that these are the areas of high risk prone areas, or these are the areas where we have the chances of happening of more number of cases. The second one is the process model, where we take different types of data sets into consideration, and then we go for the processing of those data sets, and we come up with a processed model where we can have a simulation of the process, where we can go for the prediction of the particular phenomena, that what can be the intensity if the a particular phenomena will have the exposure of different components which are influential for that particular phenomena to be happened. Okay, so actually we are creating all these. In case of process model, we are creating, or we are trying to create all those conditions which are helpful for the actually process to be happen. So by simulating all these facts, the input facts which are actually needed for that phenomena to happen, excuse me, we will be going for different kinds of simulation model. And these simulation models, they helps us in different kinds of prediction, that what will be the intensity if the phenomena will took place at the rate in which, in the partial or in the past time, the phenomena was happening. Okay, so buffer distance uh, for street buffer, streets, then clip, then we can also. So what kind of model is this? Where we apply for different proximity analysis for a street, and after that we clip out that street. Okay, after that, clipping out that buffer area, we go for the analysis that what parcel of land is falling under what class, if we go for a analysis of 100 meters of proximity analysis. Getting it? So this is what we can do with the help of different spatial analysis, modeling, and concept. Now, when we are talking about the spatial analysis, we are talking about the raster model, we are talking about the vector model. Okay, in case of spatial analysis, we have input data sets. After inputting the things, we have different geoprocessing tools. Okay, now we can go for the addition of a vector layer. We can go for the clipping of a data set. We can go for a merging of a data set. We can go for the intersect of those layers. Okay, we can multiply these raster layers. We can subtract it. Okay, so whatever is the need of time, we can go as per that spatial analysis technique. So in case of spatial analysis, we have two types of model: raster based data analysis, we have vector based spatial analysis. Now in case of spatial analysis, we used to input the data sets. Okay, now after inputting, we go for the geoprocessing of the data. And after geoprocessing, in geoprocessing, we are using all these functions which I have told you: clipping, merging, intersecting, multiplication, dividation of the rules. Okay, so after that, we will get a output layer as a new data set. You can see here in case of raster, in case of vector. Okay, clear? Then, in case of these spatial modeling, using an elevation model, because we are here going to discuss, if you see the this thing, what are the surface model and what are the different surface modeling operators. in case of this. So we are here using an elevation surface. For example, we can derive a information and identify the features that are not rapidly apparent on the original surface. Okay, so using an data which is related to their elevation or the surface data, we can easily identify the features which in original surface we cannot. So we can get the contour map, we can get the slope map, we can go for the identification of different aspect related things, where we can go for the identification of the steepest downslope direction. We can also go for the identification of different shaded reliefs, which is also called as hill shade. And we can also go for the visible areas identification, which is known as view shed. So with the help of this elevation surface data sets, we can able to identify even those data sets which we cannot identify on the field. Okay, so we can go for the uh, you know uh, uh, commands of different things into the software, into the spatial analysis, where we can opt for the contour extraction, we can go for the slope, aspect, elevation, and view shade, hill shade, these kind of properties of a particular feature identification. Okay, then we can also model the flow of water across the earth's surface, deriving its properties which are related to the runoff characteristics. We can also understand the drainage networking, drainage systems of a particular area, and we can also plan for different watershed planning in a particular area. So, based on these spatial modeling with specific analysis on the surface modeling, we can go for the identification of the contours which we cannot see on the ground. We can go for the identification of slope, aspect, elevation, view shade, heel shade in a particular area for a complete area, okay, which is not possible to identify while we are on ground. Then we can also model different water related, surface water related issues which are relating to the runoff characteristics of that particular area, which are relating to the drainage system understanding of that area, and maybe related to the basin catchment or the watershed related problems or management or planning of that particular watershed or that area. Then we have different kinds of surface models. Okay, now surface models are those models where they are representing the topography of that particular area with reference to its elevation, contour, height, and then the slope, aspect, etc. Okay, so in case of this raster data sets, we have DSM, digital surface models, digital elevation models, and digital terrain models. Now, what is DSM? Okay, what is DSM, digital surface model? Now, in case of digital surface model, it captures the natural and built features on the earth's surface. Okay, so whatever is there, whether it is natural feature, whether it is man-made feature, that means complete information about the land use and land cover classification on the earth's surface is known as the digital surface modeling. Okay, now DSM is generated using LIDAR datasets, which sends pulses of the light to the ground, and when these pulses of light bounces back, it targets and return the sensor. It gives us the range of a variable distance to the earth. So based on these backscattering observations of the particular targeted areas, we can able to get the even height of the buildings. Okay, whether it is man-made or whether it is natural feature. Okay, so lidar data or lidar system, okay, is generally used for the this kind of digital surface models to create. Now these lidars, okay, light detection and ranging systems हैं, they deliver a massive point cloud filled of varying heights, uh, or heights of the building come from the top, trees from the canopy, power lines, other buildings, and the natural features. Okay, so this light detection and ranging systems, they deliver a massive point cloud filled varying elevations. So now these lidar data sets, they helps us in getting the height of a particular building, canopy height of the trees, power lines identification, and other land use and land cover classification, which can be also called as the different cultural or built up features and natural features of the ground. Getting it? Then these DSM, digital surface models, in 3D modeling for telecommunication, different kinds of urban planning or urban utility and facility mapping, and in aviation can be used. Okay, so these are very useful in case of, because it gives us the data in 3D modeling, or for the telecommunication, for the urban planning or aviations, because the objects extrude from the earth, particularly useful in the application for identifying the abstractions. Hopefully, I am very clear in terms of these DSM, where we have studied the digital surface models. Now, these models, they captures the surface land use, land cover features of the earth surface. Now these DSM are generated using light detection and ranging systems, where based on the backscatter, this pulses of the sensor or the ground surface, we are able to get the information about the features. Now these lidars, they delivers a massive point information about the varying height values of the different buildings, where we can get the height of a particular building at the top. We can also go for the identification of tree canopy height, power lines, built ups, etc. Now, this DSM is also very useful in any kind of 3D modeling, where we have different kinds of telecommunication, urban planning related activities, and aviation related activities. Now these are the DSMs. You can see how this lidar unit, it is sending the pulses to the this thing, and this is getting reflected back from the object, and this is how these images are looks like. Now the DEM, these are different surface models and their explanations. Now this DEM, digital elevation models, is a digital model or the 3D representation of the terrain surface created from the DEM, okay, is bare earth raster grid, which filters out the vegetation and man-made features terrain elevation data. Okay, so here we are basically focused on the 3D representation of the terrain surface. Okay, terrain surface means topographical or the area of that particular area. Now created from them is bare earth registered grid, It is in the form of grids, and it filters out the vegetation and man-made features, uh, terrain elevation data. Okay, so it filters out the vegetation and man-made features. Only we can get the slope, aspect, and elevation data of the. That means we are only getting the 3D data of a particular area, which is related to the different topographical properties. Now, DEM is a bare earth register grid map which filters out the vegetation and man-made features. It is non-ground points such as the bridges, roads, buildings, natural vegetations, trees are excluded in them. Okay, whereas in case of digital surface modeling, we have all the things which are related to the man-made or vegetation features also. Whereas in case of them, we have only the topographical information of that area. So DEM is frequently used in simplest form of the digital representation of the topography. That's what I have told you right now. Now you see these surface models, okay, in case of them, is used to determine the terrain attributes such as elevation, slope, and aspect. I have told you in the initial stage itself that we exclude the these land use and land cover features. We only focus on the topographical properties of that particular area, which includes the slope, aspect, elevation, hill shade, wind shade, etc. In case of digital elevation models, the terrain features such as drainage basin and watershed, drainage networks, channels can be identified from the DEMS. So the topographical properties which are related to the different drainage densities in the areas, different watersheds in the areas, different drainage networks in the areas, and different drainage channels in the areas can be identified from these DEMS. Now these dams, they are also being very largely used for different kinds of geological analysis, soil mapping related applications, and the different kinds of hydrological modelings. Okay, so these data sets are very helpful or useful in these analysis. So when we are talking about them, you need to understand in this case, especially while we are talking about these digital elevation models, they are only focused on the terrain surface properties of the area, where we go for the dam creation on bare earth raster grids, and the vegetation and other man-made features were excluded in case of dams. They are the only representation of the topography of that particular area. So in case of them, it is used for the determination of the terrain attributes like slope, elevation, and aspects. The terrain features uh, such as the drainage basin, watershed analysis, drainage network analysis. These kind of things can be identified from the digital elevation models, and then the widely use of hydrological modeling, geological analysis, and soil mapping can be done using these digital elevation models. Rather, you can say these DEMs are very important for any kind of hydrological modeling, geological analysis, and soil surface analysis. Now, the third one is the digital terrain model, which is also called as DTM, digital terrain model. Now, it is a vector data sets which is composed of regularly spaced points and natural features such as ridges and break lines. So here you can see that this is a vector-based data set which is composed of having different spaced points and natural features such as ridges and break lines. Now DTMs, they are typically created through the stereophotogrammetries, and from these regularly spaced contour lines, you can interpolate the DTM into DEM. Okay, we can also create DEM, digital elevation models, where we are getting information about the topography based on these contour lines. Okay, we can interpolate the data sets and we can convert these DTMs into DEMs. Now, while we are talking about the different surface modeling operations, now they include the extraction of the contour lines from DEM dataset. It is also includes the extraction of slope dataset of the area. It is also, includes the aspect analysis of that area, the hillshade analysis of the area, the view shed, visibility, cut fill, and finally we can interpolate these DTMs and we can come up with the DEM model. Okay, so surface modeling operations, they include the creation of the contour lines, the creation of slope map, aspect map, hill shade, view shade, visibility, cut lines, and finally we can, in using interpolation of these contour lines, we can go for the creation of the DEM data sets. Now the different surface modeling operations includes the aspect, where using spatial analysis technique we can derive the aspect from the surface data set, raster surface data sets. The aspect, it identifies the downslope direction of the maximum rate of change value from each cell to its neighbor. Okay, so while we are talking about the aspect, it can be called as the slope direction of the particular data. Okay, so the value of the output raster will be based on the compass direction of the aspect, which can be measured in 360 degrees from the clockwise style, and from north we start from the 0 to 360. Okay, then the second one is the slope. The slope is also we can get through spatial analysis function of the raster calculators, and then we can identify the slope as it is a gradient or a rate of maximum change in the z value. Z value means x is your latitude, longitude, and the elevation from each cell raster surface. Okay, so slope, it can be identified as the gradient or the rate of maximum change in the height of a particular area. Okay, then we can also go for the contour extraction through spatial analysis. In case of contour, as we all know that they are the imaginary lines which joins the points of equal heights onto from to a main sea level. Okay, so contour represents points having equal heights or elevation with respect to a particular datum, such as mean sea level. Now these topographical maps, okay, they also shape the landscape represented with the contour lines. Okay, so based on these contour lines we can identify where there is a plateau like condition, where there is a very slopy area based on the high intensity of these contour lines, and where there is a plain surface, that also we can identify based on the shape of these contour lines. A way to describe the 3D landscape in two-dimensional ways. So these contour lines, they are a way where we can represent a 3D image into 2D. Now contour tool, using spatial analysis function, it creates a line feature class of lines from a raster surface. Okay, so it can be on 10 meters interval, it can be on 50 meters. So based on your scale of the data, we can decide the, you know, difference between two contoured lines. Okay, it can be 10 meters, 5 meters, 50 meters, 100 meters, based on the scale of the data set. Then we have Hillshade. Hillshade is a tool which creates a shaded relief from the surface raster by considering the illumination source of angle and shadows. Okay, so where there is a direct sunlight, where there is a shadowed area, so those kind of uh, you know uh, 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 this analysis we can go through with the help of the spatial analysis function under Hillshade, where we can create a shaded relief, where we can show the areas which are considered with the illumination source of angle and the shadows. Now the Hillshade raster has integer values which varies from 0 to 255. 0 represents the no data. Okay, then we have the next function as view shed, where we determines the raster surface locations visible to a set of observer, and they are useful in applications like telecommunication. Okay, so not visible areas and visible areas. So in visible areas there are a good connectivity whereas no view areas there is a problem in connectivity of different things. Then we have the next operation is spatial interpolation. Now in case of spatial interpolation, we used to take known values and interpolate them into a surface, deriving new estimated surface values. Okay, so while we are creating DEM from DTM, so based on these known values, we are generating we are interpolating those values, and or we are generating a new set of values where we are representing a complete area in terms of the those interpolated values. So elevation points interpolated to generate them, contour lines interpolated to generate DEM. Okay, so using the interpolation contour lines or the different trig heights or different elevation points, we can generate them using contour lines or using different elevation points. Using both these things, we can go for the generation of digital elevation models. Now, using these interpolation technique method, the users can create a surface from sampled locations without having visit to those places, uh, every location in the study area, which is very time saving and done in a cost effective manner. Okay, so we have given here example of digital elevation models from different contour lines or elevation points. We can also go for the generation of different population maps on base of spatial interpolation. We can also go for the creation of rainfall maps on the basis of the spatial interpolation techniques, where we have the different rainfall points and we want to show them or we want to show their spatial spread in a particular area. So we can go for the opting of these spatial interpolation techniques. Now the interpolation of technique is created a surface based sample of values with the domain, and different types of techniques are there, where we have one IDW which is called as inverse distance weighting, we have creaking, we have natural neighborhood function, and we have splines. So these are different interpolation techniques through which we can go for these creation of interpolation. Okay, so we have first IDW, where we have interpolation of raster surface from point using inverse distance weighted technique is being used. Here, the values of nearby points tends to be more similar, and the weights of the values of each point is its distance to be cell being analyzed and average the values. Okay, so here the values of the nearest points is being taken into the consideration, and then we average those values and we can have this ITW technique implementation of interpolation. Okay, then we have the second method which is called as the kriging method, where we interpolate the raster surface from the points using kriging. Okay, in third, we have the raster calculator option, where we can opt for different operations like addition, subtraction. You can see here, this is the multiplication, subtraction, addition, dividation, equals to, greater than, lesser than, okay, equals to, greater than, or this kind of things. So we can, and these are different layer. We can select this equals to maybe 5 value, then we can get a result, or we can get a output layer as that. So these are the different operations where we have gone through the different surface modeling operators with reference to DEM, DTM, and the DSM. Okay, and after that we have also gone through the interpolation technique, where we have studied 4 different interpolation techniques, which includes the inverse distance weighting, kriging, natural neighbor, and splines. And then we have also seen that using raster calculator we can opt for different operations which are related to the different map algebra expression using Python syntax inbuilt. Okay, so with this, I think I have tried to give you a very detailed study on the spatial analysis of, and modeling, where we have studied what it is, how it is being used, and what are different surface models, and how they are helpful in different modeling and analysis for different 3D analysis. So with this, I'm ending today's talk on the spatial analysis and modeling. I hope I'm clear. Now you can proceed for your quizzes, and if you have query, you can ask me now, or you can write it down and you can ask me before starting the next lecture tomorrow. Okay, thank you very much. Good day.